There is this incredibly universal feeling of frustration when you do everything perfectly by the book and the system still just yells at you.
Oh, absolutely.
Like, imagine you are baking a cake. You follow the recipe to the exact gram, you mix the batter perfectly, it rises beautifully, you pull it out, and it's an absolute masterpiece.
Right. A total success.
But then your oven just starts beeping frantically. It's flashing this red error code and refusing to shut off, all because it thinks you didn't use the built in timer correctly.
Even though the cake itself is perfectly fine.
Exactly. The cake is fine.
The oven is technically, functioning as programs,
Yeah.
but there's this fundamental miscommunication between your human intent and the machine's rigid, literal expectations.
And that tension, that clash between human intent and machine logic is exactly what we're getting into today. So, welcome to the deep dive.
Thanks. I'm really excited for this one.
Me too. Our mission today is to decode a specific software puzzle so we can understand how we communicate with the very tools that build our digital world. We're looking at a really fascinating set of notes from a 2026 presentation slide deck.
Right, by a developer who goes by the handle at Look036.
Yeah. And the presentation is titled Navigating MSVC C4702, Coroutine Generators, and Unreachable Code.
Which, on the surface, that sounds like a hyper-specific programming glitch,
Very specific.
but it serves as a brilliant case study. It's actually a story about something we call quality of implementation, or QOI for short.
Okay.
It's really about the underlying philosophy of how compilers, the tools that translate our human readable code into actual machine instructions, how they actually read and interpret what we write.
Okay, let's unpack this. Because to understand that philosophy, we first have to look at the exact moment this developer's code broke.
Right. The scene of the crime.
Exactly. Let's walk you through the real world debugging session. So, the developer was in the middle of refactoring a C++ project. It's called digraph-CPP.
Yeah, and this is a pretty classic refactoring scenario. You're in there cleaning things up, trying to make the code more readable, more efficient.
Just standard maintenance.
Right. And they were looking to add a simple convenience method called find cycle.
Okay.
And this was meant to complement an existing API in the project, which was a coroutine generator-based API called Howard.
So, for those who might not spend their weekends writing C++, a coroutine generator sounds like something straight out of Star Trek.
It really does.
What is this Howard API actually doing?
Well, think of a coroutine generator as a function that can just pause its own execution. It hands a value back to you, and then it picks up exactly where it left off the very next time you ask for a value.
Wait, so it just freezes in place?
Basically, yeah. Let's say you're searching through a massive graph structure, right? Like millions of nodes, and you're looking for a specific type of cycle. Instead of computing all 1 million cycles up front, storing them in memory, and then handing you this massive list, the generator just finds the first one, hands it to you, and pauses.
Oh, wow. So you don't blow up your system's memory.
Exactly. It's incredibly efficient for iterating through complex data.
That makes total sense. And the logic our developer wrote to use this generator was beautifully simple. They just wanted to delegate the work to that Howard generator, find the negative cycles, and return the very first one it found.
Simple enough.
Right. To do this, they used a standard C++ range for loop and a return statement. If you read the code out loud, it basically says, for every cycle you find in this generator, check it and just return the first one.
Which is clean, natural, and highly idiomatic.
Yeah.
It is exactly how you were supposed to write modern C++.
Oh.
The language is designed to let you express that exact thought cleanly.
But then they hit compile, and the Microsoft Visual C++ compiler, which is commonly known as MSVC, it threw a very specific warning. Warning C4702.
Unreachable code.
Yeah, unreachable code. And because this specific project was using a compiler flag called /WX, things went from bad to worse.
Oh yeah, the WX flag, that is a strictness setting.
Oh.
A lot of development teams use it to enforce code hygiene.
Right.
It basically tells the compiler, treat every single warning as if it were a fatal error.
So this wasn't just a polite suggestion from the compiler.
No, not at all. It was a hard stop. The build completely failed.
Okay, I'm looking at the developer's logic here, and I really have to question the machine.
Go for it.
If the code simply says, take the first result and return it, what exactly is unreachable? You look at the list, you find what you need, you grab it, and you leave.
Right.
That is just a basic early exit. People do this in programming every single day. What part of that simple sequence is considered unreachable?
Well, what's fascinating here is The compiler isn't actually complaining about the code the programmer wrote.
Wait, really?
Yeah, it's looking at something entirely invisible to the naked eye. It's complaining about code the compiler itself generated behind the scenes.
Wait, so we're getting penalized by invisible code?
Exactly. To understand why MSVC failed the build, we have to peek under the hood at how compilers translate human-readable syntactic sugar into actual machine instructions.
Syntactic sugar being those like nice readable shortcuts we type, like a range for loop, that make programming feel less like writing binary and more like writing English.
Right. A range for loop is incredibly sweet syntactic sugar.
Yeah.
But the compiler, well, it doesn't execute sugar.
Obviously not.
Under the hood, the compiler expands that simple, clean range for loop into some pretty complex iterator machinery. It basically turns your simple for each loop into a much clunkier while loop.
Okay.
And to do this, it creates invisible variables to track exactly where it is in the list. Specifically, it creates an increment instruction.
Like a counter.
Yeah, often represented as plus plus underscore underscore begin to move to the next item. It creates a condition check like underscore underscore begin not equal to underscore underscore end to see if it has actually reached the end of the collection.
Oh, I see. So every single time the loop goes around, it invisibly increments the counter and checks if it's done.
Precisely. Now think about what our developer did. They put a return statement inside that loop,
Right. They grabbed the first cycle and immediately exited the entire function.
which means the loop never goes around a second time.
Ah.
The compiler looks at this expanded code and realizes something mathematically absolute. Because of that return statement on the very first pass, the invisible increment instruction and the invisible condition check for a second pass, they will never ever execute.
Because it already left.
Exactly. Therefore, the compiler flags those invisible compiler-generated instructions as unreachable code.
That is wild. It's like, imagine hiring a contractor to build a house. And you
Yeah.
tell them you want the living room ceiling painted.
Okay?
So the contractor builds all this elaborate invisible scaffolding just to reach the ceiling. But halfway through, you realize you love the color, and you tell them to stop painting early, take their money, and go home. And then the city inspector shows up and slaps you with a massive fine because the rest of the scaffolding wasn't used.
That is a perfect analogy for what is happening under the hood here.
Yeah.
You are literally getting penalized for the invisible infrastructure the system built to execute your command.
Simply because you efficiently finished the job early.
Yeah.
But wait, people use early returns and loops all the time. If I search a basic list, like a standard vector of numbers, and return the first one I find, my compiler doesn't yell at me about dead code. Why doesn't this happen every time?
The source material highlights this exact discrepancy. This warning wouldn't happen with a regular container like a standard vector.
Why not?
With a standard vector, the compiler's analysis engine is incredibly smart. It knows exactly how vectors behave, it knows their memory layout, and it can mathematically prove that the loop body will run at most once.
So it just ignores it.
It just optimizes the extra scaffolding away without
Yeah.
complaining. But remember, our developer wasn't using a vector. They were using a coroutine generator.
Oh, right. The Howard API we talked about earlier.
Exactly. A coroutine generator uses a custom iterator. And when the compiler encounters a custom iterator, it treats it like a complete black box.
It doesn't know what's inside.
Right. Its analysis becomes highly conservative. It essentially says, I don't know the deep inner workings of this custom object, so I have to assume the worst case scenario.
Okay, so it assumes those invisible checks might be important.
Yes. It assumes those increment and check instructions might have side effects and are meant to be run. And since the return statement prevents them from running, I must throw an unreachable code warning.
Okay, so the compiler is technically right about the dead code existing. The invisible scaffolding is sitting there unused. But it seems entirely impractical.
It is.
I mean, I'm trying to look at this from Microsoft's point of view. The C++ rules likely dictate how this should be handled. Aren't they just following the rulebook?
Well, the C++ standard explicitly states that if a statement is unreachable, a diagnostic may be issued.
Maybe issued.
Yeah. MSVC is taking a very strict interpretation of that word may. They're following the letter of the law. But this brings us to the core debate outlined in the developer's notes, and that concept of quality of implementation, or QoI, that we mentioned at the start.
Right, because if the standard says they can issue a warning, isn't that technically a high-quality implementation?
Not necessarily. Quality of implementation is really about the user experience of the compiler.
UX for programmers.
Exactly. A strict language lawyer might look at this and say MSVC is 100% correct, but a practical developer looks at this and just sees noise.
It's just annoying.
The C++ Standard Committee intends for the range for loop to be what they call a vocabulary construct.
What does that mean?
It means it's supposed to be a basic foundational building block of the language. It should be ubiquitous and totally frictionless. So, warning a programmer about the invisible expansion of a basic vocabulary construct is just profoundly pedantic.
And the sources reveal that this isn't just some abstract debate, right? We actually have a compiler showdown here.
We do.
When you look at other major compilers in the industry, like GCC and Clang, they remain completely silent on this exact same pattern.
They don't throw an error
They don't even throw a warning. MSVC stands entirely alone here.
because GCC and Clang recognize the idiom. Their developers program those compilers to look at the abstract syntax tree, which is the structural representation of the code, and they understand that an early return inside a range for loop is intentional human behavior.
So they prioritize practical utility over strict, literal interpretation of the invisible boilerplate.
Exactly.
Okay, I have to play devil's advocate for a second.
Sure.
Shouldn't we want our compilers to be hyper strict? Especially in a language like C++, where a tiny mistake can cause a massive memory leak or, crash an entire system.
That's fair.
If we start ignoring warnings about dead codes, don't we open the door for actual bugs? Like, what if a programmer accidentally writes an unreachable if statement or leaves a completely dead branch of logic in a critical financial algorithm?
That is a very common and valid concern. But the source material provides a vital distinction that clears this up completely. We really have to separate two very different concepts here. Unreachable programmer logic versus unreachable compiler-generated boilerplate.
Okay, break that down for me.
Unreachable programmer logic is when you, the human, write something like if false, and then put 50 lines of critical code inside that block.
Okay, yeah.
You wrote it, but it can never run. That is almost certainly a human mistake, maybe a typo, or leftover code from a sloppy refactor. The compiler absolutely should aggressively warn you about that because it represents a flaw in your reasoning.
That's me messing up the recipe.
Exactly. But unreachable compiler-generated boilerplate, like the hidden increment check in a range for loop, is entirely different.
Because I didn't write it.
Right, you didn't write it. It doesn't represent a flaw in your reasoning. It's just harmless loop bookkeeping that the compiler forced into existence to make the syntactic sugar work.
Right.
Warning you about it doesn't prevent a bug. It just creates friction.
Okay, so armed with this understanding that this is a QII gap, a gap in the quality of the compiler's implementation, and not an actual bug in the code our developer had a broken build to fix.
They did.
If I'm the developer in this situation, my first instinct is just to tell the compiler to shut up globally. I would want to go into the project settings and tell it to ignore warning C4702 everywhere.
And the developer actually outlined that as their first option in the notes.
Did they do it?
No, they quickly rejected it.
Yeah.
Turning off dead code warnings globally is incredibly dangerous.
Yeah, that makes sense.
It throws the baby out with the bathwater. It hides the pedantic compiler noise, sure, but it also completely blinds you to those real dangerous instances of unreachable programmer logic we just talked about.
We don't want to turn off the smoke alarm entirely just because it beeps when we make toast. We still need it for actual fires.
That's a great way to put it.
So the developer had to look at option 2. They considered abandoning the clean range for loop entirely and using what's called an explicit iterator instead.
Right.
Basically unpacking the syntactic sugar themselves and writing out the loop manually, step by painful step, so the compiler wouldn't generate the invisible scaffolding that caused the problem.
And this path is a perfect example of why you shouldn't blindly restructure your code just to appease a noisy compiler.
Because it makes it ugly.
Not just ugly.
Yeah.
The developer realized that using an explicit iterator here is actually quite dangerous. It subtly changes the semantics of how the coroutine is consumed.
Wait, how does writing it manually change the semantics?
Well, an explicit iterator assumes that the generator object has a begin function and an end function as two separate, safely callable operations.
Okay.
The source notes mention that this specific generator is a pi::colon generator.
Pi, like Python.
Exactly. The pi namespace implies the C++ code is interfacing with Python bindings, likely pybind 11.
Oh, wow.
And when you mix C++ and Python, assumptions about how iterators behave get very, very tricky. Calling begin manually might force the coroutine to eagerly evaluate.
Okay, we need to decode eager versus lazy evaluation. What is the danger of eager evaluation here?
Okay, lazy evaluation is like a chef cooking your burger only after you order it. You ask for one burger, the chef cooks one burger.
Fresh and efficient.
Right. That's what the range for loop is doing. It asks the generator for one cycle. Eager evaluation, on the other hand, is the chef cooking 500 burgers at 6 a.m. and just hoping people buy them.
That sounds like a disaster.
It is. By manually calling begin and forcing the iterator's hand, the developer risks forcing the system to eagerly compute a massive chunk of the graph all at once. It would destroy the very memory efficiency the coroutine was designed to provide in the first place.
We absolutely do not want the compiler forcing our system to cook 500 burgers just to silence a warning.
Exactly.
You are breaking the entire architectural design just to stop a false alarm.
And here's where it gets really interesting, because the developer absolutely refused to compromise their design. They chose the third path.
Okay, what was it?
They decided to keep the beautiful idiomatic range for loop. They kept the early return,
Nice.
but they used a very specific surgical tool to quiet the compiler. They use a pragma warning push and pop command.
Oh, I love the pragmatism of this. For those unfamiliar, a hash pragma warning push basically tells the compiler, hey, save your current strict warning state.
Yep.
Then you tell it to disable the specific C4702 warning. You write your clean loop, and then you use hash pragma warning pop to restore the compiler back to its strict state.
It's elegant.
It suppresses the warning only in that specific file around that specific block of code.
It is the programming equivalent of putting noise-canceling headphones on the compiler, but only for one specific room in the house.
Right.
You walk into the room, ignore the pedantry, and the moment you step out, all the strict safety checks are back on.
And the source notes detail the specific files modified. It was just 2 files.
Oh.
Includes /digraphx//nashnyccycle.hpp and nyccycleq.hpp.
Very targeted.
Yeah, and what I find fascinating is what they didn't do. They didn't add the /WD4702 suppression globally in their cmakelist.txt file. They kept the strict WX warnings as errors flag everywhere else.
Which is exactly what you want.
The scoped file level pragma was totally sufficient to fix the build without lowering the security of the rest of the project.
It really is a masterful resolution, and they clearly documented their intent.
Yeah.
The pragma essentially tells anyone reading the code, and the compiler itself, I know exactly what this code is doing. I know about the invisible loop internals. They are fine. Do not bother me about this specific spot.
It preserves the canonical way to consume a generator without introducing any of those semantic risks or eager evaluation bugs.
Exactly.
So what does this all mean? Why spend this much time dissecting a single compiler warning from a 2026 slide deck?
That's a good question.
I think it really comes down to knowing your tools on a profound level. You need to understand what your simple code expands to behind the scenes. You have to be able to distinguish between the logic you wrote and the scaffolding the machine built for you.
And perhaps most importantly, you need the wisdom to know when restructuring your code to silence a complaining system is actually worse than just safely surgically suppressing the warning.
Right. Don't compromise your design.
Exactly. Don't cook 500 eager burgers just because a heuristic is being overly pedantic.
There is a brilliant quote from the source material that sums this up perfectly. The developer wrote, C++ gives you enough rope to hang yourself and also to build a suspension bridge.
I love that quote.
The generator, combined with the range for loop and the early return, that pattern is a beautiful, elegant suspension bridge. It carries the data exactly where it needs to go efficiently.
Yeah.
MSVC, in its strictness, was just panicking over a few loose threads hanging off the scaffolding.
It's a great reminder for all of us, honestly, whether you are coding software, writing policy, or managing a team.
Oh, for sure.
Understanding the literal written rules versus the actual intent of a system is what separates a novice who blindly follows instructions from an expert who actually knows how to build things.
So the next time you bake that perfect cake and the oven beeps at you, maybe don't throw the cake away. Maybe the machine is the one missing the point.
You know, if we connect this to the bigger picture, we really have to consider where this trend is heading.
What do you mean?
Well, compilers like MSVC are already this pedantic about code they generate themselves. But what happens when we start using AI to write our code?
Oh, man.
Right? Will an AI just mindlessly generate miles of clunky invisible scaffolding just to appease the strict compiler?
That's a scary thought.
Leaving human developers completely locked out of understanding their own software. If the AI and the compiler are just talking to each other to avoid warnings, the human intent might get lost completely.
We could end up with massive, structurally sound bridges that no human actually knows how to navigate.
Exactly. Who is really serving who at that point?
A perfect reminder to trust your intent and keep control of your tools. Thanks for joining us on this deep dive. Keep building those bridges, and we'll catch you next time.